We are starting the second discussion.
Right.
Observational Tests of Theory by Ian Czekala.
Hello. Thank you all for coming to the last session, and hopefully this will be invigorating before we break for drinks and dinner. I'd like to thank the organizers for putting on a really nice conference. It's been really interesting to cross-pollinate with the other half of the field that I don't normally interact with. So we're going to be talking about observational tests of theory, as Stroll has said, focusing on things that are not black holes. And so mostly meaning protoplanetary, but some planetary systems as well. And so on day one, I believe this is Roman's slide, I took a screenshot because I thought it might even be in this session. And so wanted to just touch on some of the hot CB disk related issues that we might want to think about ways we can test. And so we have talked a lot about semi-major axis evolution, whether the binary expands or contracts as it accretes. We'll have a little bit towards the end about talking about binary eccentricity evolution. Hopefully soon, if Ben is on, we might talk a little bit about accretion by which binary component, primary or secondary component. And then I think there's something interesting that spatially resolved observations of disks in particular can talk about sort of CB disk structure, misaligned disk tearing. I wasn't here last week, but hopefully Stefan Kraus had talked through the GW Ori system and some of the really exciting spatially resolved aspects of that system. And so, yeah, this was my hope to get through. We do only have about 35 minutes, so if some topics get squished, that's just unfortunately consequence of the format, and we can talk about it at drinks. But I'd like to talk first about some of the observational tests that we can do with accretion and explore how that might help us move forward with the theories. And then I think here it's Judith had provided a few slides, but I think it's really interesting to think of planetary systems as extremely high mass ratio binaries and what can we learn in that regime, especially now that we have a lot of detection techniques coming online. And then if that's going well, we have time for sort of reprising the alignment discussion that happened earlier today led by Stephen Lebau. Max Mo wanted to highlight, from what I hear, is the 30-hour-old collaboration that's now started. That's an interesting eccentricity evolution. And then finally talk a little bit more about age evolution, sort of going back to John Tobin's talk earlier in the week about class 0 and class 1 systems, which are earlier precursors to most of the systems I'll be talking about here. So our field in particular, I think, suffers from the sort of shorthand of we're talking about binaries and disks. And they're very different configurations in many cases. And so I think mostly what we'll be talking about are circumbinary disks, which is one disk around 2 stars. But very frequently in our field, a lot of studies are actually talking about this other configuration, which is circumstellar disks in a binary configuration. And so just so everyone's on the same page, it's sort of like saying you have a biweekly meeting. Sometimes that means it's every 2 weeks or it's twice a week. And it helps to know when that is if it's an important meeting. Okay, so if Ben is available, I wanted to just throw up a slide about TWA3A he provided. And I think the time series spectroscopic movies that we can now produce are really interesting, especially if we put them in context with some of the architecture of the system. So this is a recent paper we worked on combining astrometric, ALMA, spatially resolved gas observation, spectroscopic, sort of unlock the architecture of this hierarchical triple system, and then trying to sort of piece together, well, how does that time up with the accretion signatures? Ben, would you like to say a few words?
Yeah, sure. Yeah, so I think I'll just highlight the two plots here. So for the system, we had time series spectroscopy, just high resolution optical spectroscopy, great for decomposing velocity structures of accretion tracing emission lines. If you just look at the strength of H alpha on the left, you see that you have this boost in, or brightening of H alpha near periastron passage, which is consistent with increased accretion like we would expect near periastron passage. And then I'll draw your attention to the third panel, which is the one with just two spectral lines plotted near the top. So this is a accretion tracing line, helium-1 5876. And you can see that although the line is somewhat broad, we can actually decompose it into two separate structures that we can assign to the primary or the secondary. Primary is the blue dashed velocity, and the secondary is the red dashed. The mass ratio here is like 0.8. So you can see that in some epochs, we can see that there's roughly equal mass being accreted onto both stars, and then in another epoch, it's almost entirely onto the primary star. And we see that that's kind of the trend during the observations during the epochs that we have. So I think this is kind of highlighting kind of what these data can do and kind of what they can show us about binary accretion.
Thanks. Yeah, so wanted to sort of see if anyone had any thoughts or comments or questions related to accretion onto primary or secondary, and what are their thoughts on the supermassive black hole regime, and is it yeah.
I just had a question for Ben. So which orbital phases do the two examples of equal accretion versus just on one? Is it the way one would expect or not?
So in this rightmost plot here, these are from the same orbital period, the same orbital cycle. The lower one is at a phase of 0.95, and the next one is a phase of 0.98. So these are taken almost like on subsequent nights. So there's a lot of,
Can you define what you mean? What phase is periastron?
1. Or 1 or 0. So these are very close to periastron. And so there's a lot of short timescale variability. On average, we found that throughout all our observations, the primaries seemed to be accreting more. But these are only over a handful of orbital cycles that we were able to probe. So if there is some kind of precession of the inner part of the disk, we don't have the time bandwidth for this particular study to address whether it's alternating to primarily feed the primary or secondary.
Steve.
I have a basic question. I mean, what's the period of this system?
It's like 30 to 40 days, something.
30 days.
Like
so
binary period. What's the binary period?
Yeah, binary period. So
yeah, that's right. Yeah, it's like.
So it's not like DQ tau where the two stars come really close together compared to their radii. Is that right? Or
this is a similar setup. So
but it's further separated, but not that much. I guess DQ tau is 15 days. And this
yes.
30.
Yeah.
So how does it have any other differences or similarities to DQ tau?
So the main similarities, the similarities are almost the exact same eccentricity, slightly larger orbital period.
The stars are slightly lower mass.
Oh, okay.
Yeah, they're DQ tau is like, I think like 0.6 each, and these are probably like 0.3 or 0.4 solar masses each. So it's slightly lower mass, slightly more extended.
It's also a lower accretion rate system.
Yeah. Does this show much variability due to magnetospheric accretion, or?
So I think the variability that we see from night to night is it has to do with the fact that these stars have strong stellar magnetic fields that kind of truncate a potential for a stellar disk, a mini disk. So I think that part of that variability that we're seeing is the fact that these flows are somehow being entrained by a stellar magnetic field and then accreted in a way that is probably messier than what's being simulated.
So there probably aren't many disks. Is that right? Interesting.
Correct.
Like DQ tau.
Correct.
Okay.
So if you translate the equivalent width of H alpha to accretion rate, what's kind of the range?
Yeah, so we actually measured the accretion rate with U-band photometry, which is a more precise, or well, yeah, probably a more precise way to do it. And we have more data to do it. And the accretion rate we measure jumps by about a factor of 8 or so from the quiescent level to the high level, which is in pretty good agreement with the models, the 2D models from Munoz and Lai.
All right, let's take the opportunity to move on to the next. Oh, sorry, this is exactly what you were talking about, I think.
Yeah. Yep. So yeah, a little lower amplitude actually. And the phasing is a little bit off, but I think that has to do with the fact that we don't have many disks in this scenario.
Okay, so let's move on to, is Catherine here? I just wanted to talk about the slide that she sent because I thought it was something I didn't know that was capable of being studied in this detail, but there is a circumbinary disk around a white dwarf binary that goes classical nova and has sort of blown into the circumbinary disk, and it's something you can detect in outburst. And I thought this was an interesting example because it just is sort of underscoring the challenges of getting accurate binary parameters in a very variable environment. And that sort of ties into what Ben was talking about, where part of the problem here is getting the orbital elements and trying to determine binary or inclinations and so forth. And this was sort of a very different regime that is not a black hole as well. What is the period of the binary?
Yes. What's the period of binary?
I do not know. We'll have to ask Catherine.
Wait, on the previous slide, didn't it say? Go
No,
back.
it's less than 40 minutes. It's less than 1 hour. Now I'm just asking because if you are patient in 15 years, Lisa will tell you all the parameters with a high accuracy and good precision.
Okay, and yeah, Judith provided some nice slides on circumplanetary disks, and I thought this was interesting and worthwhile including one, because we're starting to detect them in real disks. This is PDS-70b, an ALMA observation, and then this is the what I think many are calling sort of the unambiguous detection of circumplanetary disk. And here are some of Judith's simulations, and maybe you might want to say a few words about sort of the suite of detectable tools that we have at our disposal. And
sure. Hi, everyone. I'm Judith Sulaidi. So we are doing radiative hydrodynamical simulations, which means that we have both density information and temperature information. Therefore, we can do mock images quite realistically. And here it just shows how we can detect the circumplanetary disk inside the circumstellar disk, basically, and that's similar to what we would expect over here. And we can do imaging in various wavelengths, and we can also have line predictions. So we did also polarized scattered light, and also we did hydrogen recombination lines, which are accretion tracer lines. Everywhere in astrophysics, they use H alpha. to measure accretion, we also try to do that. So we also can calculate from these radiative hydrodynamic simulations with some post-processing the emission lines, the line fluxes, and the variability of these objects, as well as the absorption rates. So, yeah,
Thanks.
This is all right.
Thanks. And yeah, I guess question for the audience, what sort of new physics do you think these types of observations helps probe in the sort of general binary disk interaction? Is there a regime that is sort of newly able to be explored here that may map onto black hole binaries and AGN disks, or in sort of extreme mass ratio situations? Yes. Oh, okay.
Wondering what's the accretion rate? Can you, for example, one of the things when you put this big planet in this disk, even try to determine the accretion rate is at least not clear to me. How is that determined? Is that one of the simulations? So the question then is, observationally, can you measure m dot on the planet, and then how that confound with your simulation? Can you determine the simulation, the initial?
Thanks. So everybody does the accretion calculation differently, so I can only talk about mine. We do have static mesh refinement, which means that we resolve the planet. So I calculate the accretion rate as the mass flux on the planet surface. However, most people cannot resolve the planet, so they just calculate either a heliosphere accretion rate, or some people use sinks. So yeah, but we did compare it with the observations and what they predict for accretion rates of planets, and it's roughly the same order of magnitude. So from age alpha lines. So you can relate the age alpha with the accretion rate. And there was so far 2 detections for age alpha from planetary candidates. One of them is still debated though. But yeah, the accretion rate and the age alpha is roughly consistent. Yeah.
Yeah, I was just going to ask, I don't know if we can get velocity fields from the observations at this point in the circumplanetary disk.
Yes, that'll be in a few slides, not exactly in this context, but sort of general disk structure. And so that is a very large ongoing project with ALMA, is CO and isotopolog mapping of spatially resolved disks.
Okay, and and I guess maybe that also brings up the question of, so if you're doing CO measurements, right, can you distinguish the gas from the dust?
Yes.
Is there if there's different dynamics in the dust?
Well, we're not quite sensitive to the dust dynamics because we're just getting continuum, and so yeah, it's a question of
I mean, I'm not complaining.
I have a question about the slide you showed. Are you able to explain the large dust grains that are seen in the circumplanetary disk?
Large dust grains.
Well, in other words, we see from ALMA the millimeter-sized dust, right?
Yes.
And we see the dust in the outer ring, and then we see it in the circumplanetary disk, right?
Yeah.
So that presumably there's been filtering of dust into the central cavity, and then it's entered, the small dust grains have entered the hemisphere of the planet, and they've grown so that we can see them in this picture. Is that something you calculate, or?
Yeah, so we do have dust also in full 3D in these models as well. And we see that the dust is coming in mainly from the vertical direction. If we talk about millimeter-sized dust grains, what we see over here, they come in mainly from the vertical direction with the gas. So it's bridging over the planetary gap, and it's delivered from the vertical direction. So that means this comes in with a very high velocity. Therefore, you're not going to see the stream which connects the CPD with the circumstellar disk. you're going to only have high densities inside the circumplanetary disk and inside the circumstellar disk.
But do you determine the dust sizes from growth of the dust grains, or you just?
I mean, we just use it. I mean, this is a hydrodynamic simulation, so we just set up what dust grain size we're going to use inside.
But just to clarify, there are two planets in this system, PDS-70,
Right.
B and C.
Yeah, B
The
is,
famous
B
B
is down
is
there.
not shown
Yeah.
in submillimeter. The first detection of the planet actually do not show circumplanetary disk. The PDS-70C, actually the less luminous one and near infrared shows this depth. So not every planet have this
Right.
mini
And
disk.
it is one of the challenges of interferometric imaging. And so previous study with a larger beam, there's sort of a diffuse emission around B. And so in the way that this particular image is presented, that diffuse image is too low surface brightness. And so there's some disk material there, but yeah, not as nice of a circumplanetary disk as C. Yeah.
That cannot be because that diffusive thing was way larger than the hemisphere, so it cannot be bound, right? If it's not in the hemisphere, then if it's larger than the hemisphere, then it's not bound to the object. So the C, I don't believe that because physically it's not.
The B one,
bound.
you mean?
Sorry, the southern.
Yeah,
I don't know.
yeah,
How
yeah,
do you call
yeah.
that southern one?
Yeah.
Yeah.
Good point.
So just a thought for observational tests of theory in this regime. I recall a number of works and some of my own simulations where if you look at these, a few Jupiter mass planets, depending on some of the disk parameters, you excite kind of eccentricity in these disks. So you don't have circular rings, you have eccentric rings.
Mhm.
So is that something we would expect to see? And if we don't, can we learn anything?
For this system, I don't think we have that, but maybe Stefan can say a bit about GW Ori's eccentric rings, right? There's, I believe, non-zero eccentricity measured for those, and that's a triple system inside of a disk.
Say again, what's the question is whether it's an eccentric ring in GW Ori or
Yeah, there are some models of this type of system where that, a few Jupiter mass planet excites eccentric ring rather than a circular one. And the thought was maybe you'd see this.
well, we model it as an eccentric binary with measured astrometric orbits, and with this we in Matthew's simulation can excite this broken out ring that is eccentric and is precessing around the inner triple star system.
The GWRE, the inner ring, has got an eccentricity of about 0.2. So. Hello?
I just wanted to say that there is a protoplanetary disk where there is measurable eccentricity in the dust. MWC 758 has a dust ring that has about a 0.1 eccentricity of about 0.1.
Yeah. So in this is all in the past couple of years with spatially resolved observations. So now we have at least two with pretty credible non-zero disk eccentricities.
So maybe for discussion later with
Yeah.
theorists, is that going to be explained with those models?
Okay. And so wanted to just briefly touch on the alignment mutual inclination problem that Steve had talked about earlier today. And so also sort of invoking planets as yet another probe of disk orientations under the assumption that the planets formed in the disk and that there wasn't too much dynamical evolution. Of course, that can be a big caveat. And so wanted to just briefly revisit this plot and throw up one disk that Penn State graduate student working with us, Brianna Zawodzki, has new ALMA data spatially resolved around the system AK-SCO, which is one of these short period binaries with a coplanar disk. but interestingly, it has a fairly high eccentricity of about 0.6. And so Brianna can chat with you more throughout the rest of the workshop. But this is sort of a system where we're now trying to sort of drill down into understanding why is there a large cavity? Why is the ring have a sort of non-uniform azimuthal brightness distribution? There's some interesting scattered light data. There's some interesting CO kinematics data. And so this is sort of a compact binary where we're actually kind of getting all of these interferometric orbits together kind of thing. But just wanted to throw that as a, not necessarily counterpoint, but Steve had sort of drawn your attention to these polar disks. And so I forget who made the comment about what if the disk is just sort of born in its polar orientation. I mean, the same can happen for a disk that's just kind of born in a coplanar distribution. Why did no inclination evolution happen here? And so also that sort of leads me into two questions that Cristiano Longarini and Simone Sepe sent to me. And sort of the first one, maybe you might want to field questions after I introduce it, is if we suppose that the initial distribution of disk inclination and stellar eccentricity is nearly random, why don't we see a lot of disks in a polar configuration? And so I guess the debate can be, well, should we be assuming that it's random? Is that something that makes sense from a star formation, the way we understand how star formation proceeds? And then if yes, what is the dynamical consequences of that?
Maybe I can start. I mean, from the cluster simulations, you can look at distributions of disk inclination relative to orbital inclination and stellar eccentricities and so on. And something I haven't done, but in theory, you could then try and think about how they evolve due to these polar alignment processes and so on in subsequent evolution. So maybe that's something that should be done.
Cristiano or Simone, any thought, anything you'd like to add?
Yes, well, the point is that, as we discussed before, the highly inclined disks that we see in your plot from the paper in 2019 are all around a system with more than 2 stars. Pure binary has just coplanar configurations. Even if we expect that, I mean, I'm not sure about that, but it seems reasonable that the initial condition should explore also the mutual inclination higher than the critical angle for polar alignment, and I mean not just coplanar system. And so there are 2 problems, or maybe 1 problem: why they all have the time to go coplanar, and the one that are over the critical angle don't go polar.
Thanks. And your second question that you sent got me thinking. So I dug through some of the tables that I had, and it actually turns out, so the question is how many young binaries we observe with disks actually have a tertiary or quadruple companion, or are actually higher order multiples. And it's actually pretty significant. It's like a third. And this is just a subset of all the ones that I know about. I'm sure those of you who do direct imaging surveys and so forth might have a better catalog, but this may be an interesting thing to think about from the star formation perspective. Yes.
I'll let Max can answer, but
Yeah,
I don't think that number is surprising. If you just drew randomly from the population, this is not the wrong number, right?
Not all of them are very tight spectroscopic.
No.
binaries.
If they were all tight
Yeah.
spectroscopic binaries, the number would be much higher.
Yeah.
But observationally, we're biased towards more massive disks and gas, and more massive disks and gas are the ones that are most likely to make binaries and triples and higher order multiples. So there's I think a underlying correlation there. Makes sense.
Thanks. Dong, do you have a comment?
So about this first bullet point, and this binary, like AU separation, are supposed to have undergone migration during the class 0 phase, according to Maxwell. I think it's very convincing, I think, right? And they are most likely undergo migration and then probably experience some circularization. So most of them are, okay, so like in the disk that you see, I imagine they sort of another episode of fallback, sort of assembly of that's sort of my picture. You have this binary undergo class 0 migration, class 0 phase migrate, and then of course you few gas coming in, and another thing, right? So they could be, depending on how the next episode of mass info, you could imagine the coplanet or
yeah,
right, and
we probably won't have time for it, but this was John Tobin's plot from earlier this week, where I thought, this is the stage where we really need to invest more observational efforts to sort of answer these questions and put together a timeline of how the populations are progressing. And this is something that has been hard for a long time, but people are starting to make progress on it. Okay, Zoltan.
Yeah, sorry, I'm just getting tired, so I have a semi-brain dead question, which is there an analogy of the AGN disk channel here, where there's two planets going around the star, and would we know? Or do we expect any? Has anybody simulated that?
Is there a binary planet?
Yeah,
is what you're saying?
Just to scale the previous section.
I know of binary asteroids and
yeah. So they're, but mass ratio wise, it's more extreme. But in principle, you could make a stable binary planet, but nobody has seen one. It probably means they don't exist. So there's been quite a bit of interest in looking for moons, like satellites around transiting exoplanets. And so I would say the non-detection of those things suggests that there's not a whole lot. Does somebody want to disagree with me or add to that?
I'll just say that Pluto Charon is almost a binary planet, probably.
Yeah,
that's not the issue. There's tons of binary Kuiper belt objects with a wide range of mass ratios. The mass ratio of that system to the central object is much more extreme than the AGN case, I think, is the issue.
The other point, of course, is that transiting planets all tend to be close, and then the Hill sphere will be small. So if you are going to have binary planets, they're probably at wide separations, and they're not going to be transiting.
Yes, I think that's true. That's true. Those are the hardest ones to find.
We have a question on Zoom. Alex?
Yeah, just a comment on this. I don't follow this too closely, but I thought I remembered the first big exomoon claimed detection. I thought that was a pretty large mass ratio, so maybe it could fit near this categorization.
Claimed detection.
Okay, so
right.
Oh, sorry. Yeah.
Actually, there is two. The second one just got published by us in Nature Astronomy. And both of these cases are, very, very large moons, like Neptune mass or this kind of thing. So in these cases, it's very, very, very different than what we see in the solar system. However, we also have to understand that circumplanetary disks are forming beyond the ice line. That's the reason why we're now going to find a lot of moons around closing planets, because there are no satellites also or not many satellites in the solar system within the snow line, because there is no circumplanetary disk formation there.
Okay, thanks. And in the remaining time, I want to try to have 3 people comment. One, if Rajika Kurwita is online, I know she has some publications related to long-lived circumbinary disks, and was wondering if you might want to comment on any of the discussion about sort of evolution of these systems. And
yeah, so I guess I briefly mentioned it. I was looking at the multiplicity of disk-bearing stars in Upper Scorpius and Upper Centaurus Lupus to kind of see if the multiplicity varied between protostell classes and the main sequence, because if the multiplicity was higher for the disk-bearing stars in the protostar classes than it was in the main sequence, then we would think that the multiplicity made the disk disperse faster. Or if it was lower, then maybe the multiplicity made the disk live for longer, but we actually found the multiplicity was about the same. But the thing is, the observations, I wasn't distinguishing between circumbinary disks or just disks in binaries. So that can complicate things a bit, but it seemed like in general, for the stars that I looked at, which were like FGK type stars, the disk lifetime probably doesn't vary too much between like single stars and multiple stars. But again, that wasn't distinguishing between circumbinary disks and disks and binaries. So it would be interesting to investigate this.
Can I ask a quick follow-up on that? Is that consistent with this seems different from the work that Adam Krauss published a few years ago showing that infrared excess declined precipitously for, modest separation binaries compared to wide binaries and single stars. So I'm wondering what's different.
Yeah, so I think the Krauss paper you're mentioning, I think you were saying that when you get to 40 AU or something, the disk frequency drops a lot, and that's like a region where we think it might be really hard to have disks. So that was part of the motivation where like the circumstellar disks are smaller, but there was also like the Harris paper from 2012 and Cox 2017, I think, that were looking at, I guess, disk fluxes at different separations. And yeah, you kind of see that when you get to smaller and smaller separations, like the dust gas or whatever that's being measured decreases. But then there are these circumbinary disks around the closer binaries that were quite just massive. And so I was, yeah, it's kind of hard to figure out what the deal is with circumbinary disks, because like I mentioned before, we know of some circumbinary disks that are very long-lived and they're just big, and it's just a bit weird why they're so long-lived, like why they have ages that are much longer than a typical protoplanetary disk lifetime. So it's just a bit complicated, but I think the general consensus that, for tighter binaries in the circumstellar disks are obviously disrupted because they're truncated, but for circumbinary disks, I'm not quite sure what the deal is. And it'll be interesting to figure out why the circumbinary disks seem to live longer and hang around for longer.
Thanks. Okay, so very quickly, wanted to just give a snapshot of the CO mapping that we're able to do now with ALMA. So it's sort of a 300 meter per second slice that we're able to sort of tomographically reconstruct the disk velocity field. And so this is just CO, but we have isotopologues and things like HCN, and so you can get different layers, and there's sort of an active area of research for searching for protoplanets is sort of the main driver, but maybe Josh might want to say a few words about his work with binaries, undetected binaries, as evidenced in sort of scattered light here, but also gas kinematic features and ways to probe, presence of binaries through disk features.
Yeah, well, this particular source here, MWC758, is the one that I mentioned before that has a measurable eccentricity in the dust ring. And it also has these two very prominent M=2 spiral arms, which in the past has been associated potentially with an outer planet outside the spiral arms. But if you look in the bottom left panel there, the spiral arms tentatively wrap around quite tightly. So that would imply that you have the origin, whatever's perturbing the spiral arms is probably inside the cavity. So there's a gas depleted cavity, there's a dust depleted cavity in the source. But the mass ratios here is it's definitely not in a binary regime. The central object's about 1.5 solar masses and the companion's about 10 Jupiter masses here that I proposed. But the kinematics are a very good way of probing binarity, because the perturbations that you see in the velocity field are directly caused by the perturbing body, and they get larger obviously with the mass of the body, and you start generating eccentricities in the gas flow, which is also something that we can potentially measure with ALMA if it exists.
Thanks. And let's carry discussion for that one over drinks. And last but not least, let's let Max and his newly minted collaborators talk about this project to close out the session.
Thank you. So yeah, Chris Feedy showed this plot yesterday. I've been obsessed with it. This is showing the eccentricity evolution of binaries, circumbinary disks. I think it was noted that E dot crosses 0 around 0.08 and 0.38. But what I noticed studying it again is that E dot also approaches 0, gets close to 0, around E equals 0.18. And so this is actually going, if you model this forward, it actually predict a trimodal eccentricity distribution for stellar binaries at those values where E dot's small and deficits at E equals 0.13 and 0.3. And I was asked this morning, should we trust these results of 2D simulations? The answer is simple. You just compare their predictions to observations. Next slide, please. And so in black, I'm showing the observed solar type Kepler eclipsing binaries with periods of 20 to 400 days in the black histogram there. And the blue, I'm assuming that proto-binary started with this Rayleigh distribution during this embedded class 01 protosolar phase, when the mass of the disk is much, much larger than the mass of the proto-companion. Actually, if you look at giant planets, we see the same distribution. Giant planets are also accreting in this regime where the disk mass is more massive than the secondary. But eventually the disk mass gets depleted, and then you transition to what this T-Tauri phase, where the secondary is more massive than the disk. And I think this is where the eccentricity evolution we saw in the previous plot is occurring. And so if you forward model the eccentricity evolution according to those simulations, you see that trimodal eccentricity distribution emerge. With the data, I don't know if I trust if it's significant, that dip at 0.3, but the dip at 0.13 is huge. It's so obvious. If I were just to interpolate that first bin and third bin, I would get that little green band there. And so the difference between the green band and the measurement is 5 sigma. Yeah, between there and there, there's just a deficit there that's really obvious. And so, yeah, I just want to thank the organizers for bridging the gap, bringing us together. People like me working on stellar mass binaries and theorists of binary black hole accretion.
Okay, so we'll see the paper on the archive on Friday. All right, and let's, I guess, call the discussion section there. Thank you, everyone, for your participation, and especially thank you for those that provided slides and sort of led some of the discussions. Really appreciate it. Thank you.